my ultimate VHDL PON tutorial. And in this video, we're going to be going over the complete circuit for the implementation of the VGA controller and the graphics, which is the PON game essentially. And so I'll be talking about each individual block of VHDL code that we interconnect using logic lines and buses within our HDL designer software. So I'll blow up the image here with the circuit so we can see it a little better. And I'm actually going to break this into two videos. For video number 3 for this video here, I'm going to talk mostly about the VGA controller side, which is the upper half here. And then for part 4, for video number 4, I'll talk more about the implementation of the graphics, which is the bouncing ball and the 2 paddles for the PON game, and how they work together to display on the screen. So I'm going to talk about each of the individual blocks, the HDL blocks, and talk about their inputs, and how they work together to create the overall goal of this VGA controller circuit, which is to create our H-sync signal, our V-sync signal, and also our V-display and our H-display. And so I'll talk about those signals just to give you a little clearer picture as to what their purpose is and what they're used for. So again, essentially we have our H-sync and our V-sync, and those two signals together, based on how we formulate them, we can control different resolution settings that will be displayed on our VGA monitor. So together they essentially create the zigzag scanning pattern, which dictates the number of pixels that we have on the screen, on the surface, on the horizontal plane, and also on the vertical. It also creates the frequency of the scanning process. So the screen refresh rate essentially is the speed of that occurring is also dictated by the frequencies that we send in on our H-sync and our V-sync. So that was, again, when I mentioned that it's good to look at the H-sync and V-sync as almost like an X and Y coordinate system. And that comes into play, that analogy comes into play when we get into more doing work with the paddle and the ball for the PON aspect of the game. So, but anyhow, for now, this zigzag scanning effect is essentially created by H-sync and V-sync. That's pretty much the whole purpose of it, is just the pattern, the scanning pattern, and the frequency of the pattern, and also which essentially, again, dictates the resolution setting, so the number of pixels we have on the horizontal plane and the vertical. And that's all based on these two signals here, H-sync and V-sync. And so now, the H-display and the V-display. So I'm going to talk about, you've probably heard the term vertical blanking or horizontal blanking. And that essentially is the beam, the electron beam that controls the color. Well, the movement of it actually starts from coordinate 0 and will scan across. And then when it reaches the end, it has to jump back to the beginning. Well, the reality is that the beam doesn't shut off. So the beam stays active. And so in order for, when the beam is retracing back to its original spot, it's actually staying on, and that beam is actually active. And so there's a retrace period there where the beam is actually traveling back to its starting point, and it is actually active. And that's called, the term that's used to describe that is called a raster scan. And so that's this pattern here. And so these little lines here, that's actually the pattern that our electron beam for RGB is the pattern that it will leave if we don't disable the beam from displaying any information. It will actually display this pattern on the screen. So in order to prevent these raster scan lines from appearing on the surface of the screen, what we do is we call, during that time period that it's traveling back to its starting point, we actually disable any information from coming through on our RGB lines. So essentially, these two signals here, V-display and H-display, those signals essentially, all they do is tell us when these particular lines would be active. That's essentially all these lines are for. So it allows us to shut our RGB lines off during the time period that this raster scan occurs. So it's jumping from its endpoint back to the next line. So during that scan process, we can disable the screen so that we don't get these lines appearing on the screen. We have a perfect picture, and the graphic RGB signals are only displayed on those particular pixels that we wish to have color appear. So during that retrace period, the RGB lines are inactive. So that's the whole purpose of V-display and H-display, is just to shut off our RGB signals during this raster scan period. So this is the pattern here, what it looks like. So we have, for our horizontal, it's constantly jumping down one row to the next. So this line here, all these pink lines, that's our retrace on the horizontal. And then this black line here, that's the retrace for the vertical. So when it gets down to the last row on the horizontal lines for our screen, it will jump back to the top coordinate 0, 0. And so that black line there, that's for the vertical retrace. And that's the whole purpose behind the V-display and the H-display. So essentially we begin with our 50 megahertz clock signal. This originates from our development board, so in this case the Altera D1. We take that and we run it through a simple VHDL clock divider, and that should be a snap for you to implement. It should be pretty straightforward. And we then create a 25 megahertz clock signal, which we use to drive 2 separate mod counters. So now we have a mod 800 counter, which we use to handle all of the horizontal aspects of our VGA controller circuit. And then we have a mod 525 counter, which we use to handle all of the vertical aspects of the VGA controller. So I'm going to bring in a couple of diagrams here. I've got a mod 525 counter, essentially like a timeline. Try to view these as counting states on a timeline. And you're going to see this in a couple of the diagrams that I'm going to bring in. So now, the fact that we use state 0 as a valid state on both of our counters, so we've got a mod 800 and a mod 525. The fact that 0 is a valid state, that means that we only need to count to 799, because state 0 is a number, a particular state, we do one less for whatever value of the counter that we're counting up to. So just keep that in mind, remember, when you're implementing that. So we've got a mod 525 and a mod 800. Now, you're going to notice that at different points I've got a repeating state. So the fact I've got state 653 here on the mod 800, and I've got state 653 at the beginning here as well, all that indicates is that the pattern is repeating. So there's just, these are the two, the fact that the numbers are the same, state 653, these are the same state. They're just on different points on the timeline. So it's just indicating that the cycle is repeating. And I've got that as well for the mod 525 counter. So you can see here for state 491. So it just simply indicates that it's a repeating pattern. So just keep that in mind. So essentially we have this timeline for each counter, and the states are counting through. So we've got a mod 800 and a mod 525 counting from state 0 through to 799, and for our mod 525 we have from state 0 all the way to 524. So now it's counting through those particular states regardless. So whatever they're happening, they're going to occur regardless of what we do. So they're counting away. Now the fact is that we need, in order to create these H-sync signals, we need for the horizontal aspect of the circuit, which is our H-sync and our H-display, we need to have specific signals, momentary pulses, so a set and a reset signal sent out on specific logic lines for us to use in order to drive a latch circuit. So I'll go back to here. So I'll go back to the state machine, and for the decoder aspect of it. So we need to have 4 separate output lines rise high for a momentary pulse, so a single clock pulse, logic high of 5 volts for a specific state on each of the counters. So we've got a mod 800 counter. So at various points between 0 and 799, we get to dictate which of our 4 output signals will create a momentary pulse for it. So now I'm going to bring in this diagram, which I have included on the webpage for your review. And this diagram, what I've done is I've actually added the mod counter states that I brought in earlier that show the different states essentially like on a timeline, and how they relate to the actual signal in question that we're talking about. So here we've got our horizontal sync pulse. And so I think this helps, and this shows the different states and how they relate to the highs and lows of our actual signal output that we're talking about. So as you see, how each state will relate, and essentially that's what the latch circuit here that we're talking about. So our decoder state machine, all that those state machines perform, their task is to create momentary pulses along a specific point on the counters, and then we use those as they travel through on the timeline. We use those clock signals to drive the state machine, which is essentially, in this case here, we've got a horizontal sync output, which is logic 0 volts, logic high volts. So it's a single logic line, our H-sync right here. And so based on different states, we can dictate, depending on how we encode our VHDL here for this latch, essentially a latch circuit state machine, we can dictate when the logic pulse will go low and for how long, and then when it will rise high again, and then how long it will remain in a logic high state until it repeats. And so as you can see here, I've actually indicated where the pattern repeats, and I found that a lot of students got confused with this, and they were actually thinking there were 2 separate pulses, and there was some confusion there. So this is actually the point where the pattern repeats, and that's where I talked about how the state is the same as the 2 different areas on the same timeline. So it's just indicating that the pattern is repeating. So just keep that in mind. And so the combination of those specific signals coming from the horizontal decoder state machine and the latch circuit state machine interpreting those signals, we're able to generate specific timing requirements for specific outputs. So we have our H-sync, as you can see here, and by implementing that to various processes within the latch circuit, so 4 separate processes, as I mentioned, due to the fact that we have 4 separate output lines, we then are able to create specifically controlled signals with specific timing requirements. And so we have our 4 signals here, which dictate our specific resolution setting and display for our VGA monitor. So the last 2 things I'm going to be talking about in this video is the RGB combination circuit, and I'm also going to talk about this horizontal decoder reset line. So essentially the RGB combination circuit, all that is essentially is a series of AND gates that are interconnected. We have 3 separate AND gates, one for each of our RGB colors. So now, depending on the number of RGB signals that we have, essentially determines the number of inputs to our AND gate. So the fact that we have 3 separate RGB signals, one for the ball and one for the paddles, one for paddle 1 and one for paddle 2. So in total we have 3 separate RGB signals for RG and D. That means that we have an AND gate for all of the reds, so we have 3 inputs to an AND gate for all of the reds, and another 3 input AND gate for the green, and another 3 input AND gate for all of the blue signals. And we then essentially control the activation of those AND gates based on when V display and H display signals from our latch circuit, when those 2 signals are active. So we essentially combine V display and H display signals into a 4th AND gate, a 2-input AND gate, and that essentially interprets when our RGB lines will be active. And so that's pretty much what the RGB combination circuit entails. It's just all it's doing is allowing RGB to be active when V display and H display are both in a logic high state. And so the last thing that we're going to talk about here is this horizontal decoder counter reset line. So essentially all that is performing, that logic line is acting as an enable for the mod 525 counter. That's pretty much all it's doing. So as you can see here and how it counts through on the horizontal planes through all the horizontal pixels on the screen, starting from coordinate 00, and it's counting through all the various pixels on the screen, and it reaches the last coordinate on the horizontal, and then it needs to jump back to the beginning of the counting sequence, but move down 1 on the vertical. That's what this particular line here is doing, just allowing the mod 525 counter to increment once to move down onto the next row for the horizontal count sequence. So that's all that this is for. So you just make sure that it's coming from the horizontal decoder, and then this particular mod 525 counter will increment when it's supposed to. So that sums up video number 3 for the VGA controller, and in video number 4 we're going to dive into the display process implementing the Pong game, and that's these 3 blocks here, and I'll be talking about those